Today we are talking about properties of logs. So we looked at how to use logs. We've examined what logs are. Now we're going to look at a few other parts of it. So change of base formula. Now this is very helpful for non-Desmos calculators. If I'm using a TI-84, change of base is going to be my best friend. If I'm using Desmos, I don't need to use change of base, but I can if I wish. So if I know my base of my log is A, so I'm doing log base A of B. In order to do that in the calculator, I could do the natural log of B divided by the natural log of A, and that will actually end up calculating it as log base A of B. So over here, it's wanting us to evaluate log base 8 of 20. So that's all done in the calculator. I'm going to first do it with change of base, and then I'm going to do it just writing it with the base. So here with this, my change of base would end up saying the natural log of 20 divided by the natural log of 8. And that's all I need to put in the calculator. So there's my Desmos. So let's get that nice and big for you guys. And projector mode. So if I do the natural log of 20 divided by the natural log of 8, this is what we get. This is exactly the same as if, remember, I showed you how we could do a different base on the Desmos calculator right now by going to functions, miscellaneous, and it has log base A as its own function. So if I do that, I can put in 8 as the subscript in there and 20 here. Exact same answer, right? So just sort of proof of concept that yes, this change of base works. So at the end of the day, look, if I knew we had to use the TI graphing calculators, I'd really have to stress this. If you like typing it this way better than this way, I don't care. If you like this way better than that way, I don't care. They both give you the same result. So whatever is most comfortable for you, type it into the calculator. Just go with it. Now, the big properties of logs. These are very important. I'm going to explain why they can be so important. This all comes down to ease of calculus. So when I'm taking derivatives or doing integrals in calculus, taking the derivative of integral in something in this form where it's log base A of u times v may be more difficult for me than doing log base A of u plus log base A of v. When things are separated by addition, I'm allowed to take the derivative or integral of each piece separately. And it could end up becoming easier in calculus to say, wait, instead of having this more complicated log like this, it might be easier to take the derivative of an integral when we have it in this expanded out form. Then we can do all our calculus and then recondense in the end instead of having one long answer that has all these different parts. We can recondense it at the end. So it may seem silly, like, why am I going between this condensed form and expanded form and back and forth? Trust me, when you get into some more complex calculus, it can be very helpful to split these up. So if you have things multiplied inside of a log, they can be split as addition. This is a two-way street, though. If you had two logs of the same base, they must have the same base. If they had different bases and are added together, nothing you can do. But if the bases are the same and they're added together, you can bring what's inside of each log together being multiplied together. So I'm going to very quickly show again how this can work if I put real numbers in here. So if I say the natural log of 2 times 10, that's this. If I say the natural log of 2 plus the natural log of 10, again, I get the same answer here. So I just kind of want to show you that, yes, that does indeed work. So multiplication gets split with addition. Division, the opposite of multiplication, gets split with subtraction, the opposite of addition. So if you had the log of u divided by v, you could do the log base a of u minus the log base a of v. Again, if you're looking to condense it, if the two logs of the same base are being subtracted from each other, the first log is going to be your numerator, second log is going to be your denominator. And the last property says that if you have an exponent inside of your log, like we see here, it can come out in front. So basically, I bring that power out front as a coefficient. If we wanted to do the reverse, if I have a number out front as a coefficient, I can bring it inside as its power. Those are our properties. Those are our three big properties we're going to use. And not too bad, right? You know, it will take a little bit of practice to fully get them down, but they're not that hard. Multiplication splits to addition. Division splits to subtraction. Powers now become, or exponents now become coefficients. That is a summary of the whole thing. So to expand something, we want to rewrite the problem as a series of simple logs added and or subtracted. So like I said, if I'm looking at this, this may be easier in a calculus sense to look at this as three different entities that we're each either going to integrate or take the derivative of. So here with this, I have the ln of x times y to the fourth, all divided by 2. I'm going to do this in 2 steps, but honestly, if you can see doing it all in one, great, good for you. And that's absolutely fine. Just skipping that. I want to do it in 2 steps just to make sure we're seeing absolutely everything. So x times y, that's addition. So I can say the ln of x plus the ln of y to the fourth. Now it's all divided by 2, so I need to say minus 2 or ln of 2. Sorry. Now, the one thing I didn't do here was deal with this 4. I see 4 is my exponent on y, so I just want to bring that out in front. So that gives me the ln of x plus 4 times the ln of y minus the ln of 2. Now notice each of these expressions, each of these terms is incredibly simple. ln of x, 4, ln of y, and ln of 2. There's nothing crazy inside of our logs. That's how I know this is an expanded form. So look, if you saw when you were already splitting and you knew you were about to write this ln of y to the fourth, and you go, oh, that 4 needs to be a coefficient, goes from an exponent to a coefficient, and you just jumped straight to this second line here, not a big deal. Not a big deal at all. I just included this middle line to kind of delineate the 2 different ideas. a little bit and just to help with you guys, but not bad, right? Okay. Now here, to condense a logarithmic expression, we want to rewrite it as a single log. We only want the log of just one simple thing. Or sorry, not one simple thing. We want just one log. What's inside may be complex, but just one log's all we want. Okay, so again, right away, I'm going to do this two-step. If you can see how to do it in one step, great, good for you. I do want to just make sure we're seeing everything here. So the first thing I'm seeing here is I have coefficients. I want to bring them as my powers here. So this will be the log of x cubed plus the log of x minus 1 to the 4th power. So all I did was make my coefficients now my exponents. Now I see subtraction in here with the second one, but that subtraction's inside the log. I can't do anything with that. I need the subtraction to be outside the log to change it to division. I do see between the logs are added together, so I just want to multiply the insides. So I can now say the log of x cubed times x minus 1 to the 4th power. Now, honestly, at the end of the day, bless you. If you need tissues, just grab them, okay? Sorry, just email me off slightly. At the end of the day, you could multiply this all out if you really wish and have one long polynomial in here, but I'd say that's very unnecessary. This is neat, this is clean, and I understand what it is. So I would just leave it at this. I would not bother multiplying out what x minus 1 to the 4th power is, and then multiplying x cubed by that. That would just be overkill. This, I say, is a simple, clean expression with simply one log, so we're good. Any questions on this so far? I'm not seeing anything in the chat, and look at faces in the room. It's looking like, yeah, we got this. This isn't too crazy. Now, here's the last idea we're going to do, and this is an interesting one. This is a very interesting one. This is an application of logarithms. This one's a little hard to see. I'm not going to be like testing you hard on anything like this, but it is an interesting application that I do want to expose you guys to. So one way to find a model for nonlinear data is to use the natural log of both your x and your y values. And if the points graph all in a straight line, then we actually know the natural log of y is equal to the slope times the natural log of x. And then we can utilize our properties to mess with it from there. So this data here looks crazy, right? Like, I'm not seeing any pattern here, are you? No, so here's what we're going to do. I'm going to take the natural log of all my x values and then the natural log of all my y values. And I'm going to rewrite them in a new table. Natural log of x, natural log of y. So, yeah, I know this data looks crazy. We'll oh, actually, I'm going to do it this way. So here with this, I'm really going to take advantage of Desmos here. So I'm just going to type this data in here, just how it is. 389, getting all my X's in first. 20.086 and 54.598. I got these Y values here. 7.389. 54.598, 403.2 or 429, and geez, this number is big. $958. Okay. So if I zoom on this data by hitting the magnifying glass, interesting. Okay. It looks like maybe this might be like a slow moving exponential. I don't know. But, you know, I see some pattern to those dots. What I can do here, so I said, let's take the natural log of both. So I could do the ln of x1. That gives me these values. Now notice these are incredibly close to whole numbers. This is almost 1, 2, 3, and 4. I will round those because they are all extremely close. And I know my numbers were probably rounded decimals to begin with. If I do the ln of y1, I get this. So, okay, now I got new data here. Again, these are extremely close. I'm just going to round to that whole number. So, instead of taking the ln of each individually, I just used the table feature and said the ln of each heading. I could have just taken the natural log of each value individually as well. So this for x now appeared to go 1, 2, 3, 4. And then for y, this looks like 2, 4, 6, 8. So what am I doing here each time? Am I adding to? 1 to 2, 2 to 4, 3 to 6, 4 to 8. Multiplying by 2. So here, since we have a pattern of multiplying by 2, I could say the ln of y is equal to 2 ln of x. Well, using the properties we just learned, this 2 can now become an exponent. So the ln of y is equal to the ln of x squared. Now, both of these are in ln's. Do the ln's seem so necessary right now? Exactly right, because they're both natural log of it. The head shake saying, nah, they're not necessary is right. So this actually becomes y equals x squared. Okay. Okay, if I did almost 3 squared gets, okay, that's not bad. A little over 7 going to 54. Well, 7 squared is 49. Okay. 20 squared, well, slightly more than 20 squared being slightly more than 400. Okay, that makes sense. Now 54 squared, we're not going to know that off the top of our head, so I'm not worrying about that. Let's take a look. I'm going to turn off my natural log data and just look at these green points here. So I was told the equation is y equals x squared. Wow, it hits them, right? So this it worked for us. This data did not necessarily look like y equals x squared right away, right? This data looks like, what is going on here? But it actually was. So I don't think I assigned any homework related to a problem like this. Just wanted to show you an interesting application. So just back to the Smart Notebook file. Here's the homework. 40 on pages 207 and 208, 48 through 58 even. I believe those are our expanding problems. And I believe 70 through 80 even are the condensing. I don't think I had them reversed, but basically one group's expanding, one group's condensing. That's all we need to practice. So stop recording.